Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. My name is Franck Marchis. I'm a senior researcher at the SETI Institute, and today we are going to talk about Mars, and specifically whether or not this planet was one day a good place for life. And for this, because as you know, I'm not a Martian guy, I don't know anything about Mars, we invited a SETI Institute researcher uh, called Kaveh Pahlevan. Hello, Kaveh. How are you?
Hello, good.
Good. Where are you calling us from?
Oh, I'm in Washington, D.C.
Okay. Well,
So,
I'm in San Francisco. I'm in Mountain View today. You may
mhm.
notice I'm at the institute, and yeah, thank you very much for joining us. I mean, it's a great time to talk about the potential of life on Mars. So, Kevin, you are being leading a team that did some modelization of an early time on Mars, and basically you think that Mars, primordial Martian atmosphere, was quite different and 1,000 times denser, made a different type of composition. And because of this, the planet was warmer. And we are going to talk about this in more details. But I remind to our viewers that they can tell us, first of all, where they're watching us from, and also get ready to ask questions directly to Kaveh about Mars. Okay, so Kaveh, I'm very sorry. Again, I'm not a Martian. When I see picture of Mars, it looks kind of a dry, cold, desertic area. I mean, we sent ton of spacecraft over there. I did not see any aliens, any city, any green species, not even microbes. So now you are telling us that one day Mars was an hospitable planet. Could you tell us a bit more about that, please?
Yeah. So I should preamble this by saying that I'm not a Martian either, but we started looking at this problem when we realized that all of the current approaches to understanding Mars's climate, start from the present and sort of propagate back in time, like how fast is the atmosphere being lost and so forth. And so what would have been there, in the past. And we realized that there's another approach that hasn't really been well explored, which is starting with what we know about how Mars formed and developing the story forward. And so what we found was that this primordial atmosphere, the atmosphere that Mars had right after it formed, not only was composed of water as was expected, but also of significant amounts of hydrogen, molecular hydrogen, two hydrogen atoms bound together. And surprisingly, we found that we could link this initial composition to measurements that are being made by the rovers. So Mars Science Laboratory, made observations of clays on the Martian surface that form much later, but we think that we can link what happened very early on Mars to the signatures that are recorded in these clays. So
Okay. So before we continue, thank you very much, Moon, for the super sticker. We have people watching us right now from various places. I'm going to name a few of them: Vancouver, British Columbia, Tehachapi in California, Central New Jersey, Chapé in Quebec. I say the French way, I'm sorry. Hamner Springs, New Zealand, and in Germany, a city I can say, I'm sorry, Antwerpen, and someone from France as well. So welcome. You are watching a SETI Live with Kaveh Pahlevan, and we are talking about Mars and the past history of Mars, whether or not Mars was an habitable planet. Okay, so you mentioned that this study has been basically it's a model, first of all, right? You basically developed a model of the atmospheric evolution of Mars.
Yes.
And then you find some indication that Mars could have this type of atmosphere. So can you tell us what indication you have used for that? What's clues?
Yeah. So the one thing that we realized as we were developing this model is that the main volatiles that we expect early on in planetary atmospheres, water and hydrogen, behave very differently. So water, on Earth, we're familiar with water condensing in the lower atmosphere and the upper atmosphere being very dry. So the stratosphere, where most of aviation happens, is very dry. That's partly why we go to the stratosphere. And we noticed that that when water condenses, it effectively gets cut off from being lost from Mars's atmosphere, whereas molecular hydrogen is very volatile. It never condenses effectively. It never forms clouds. And so molecular hydrogen can rapidly escape from any planetary atmosphere. Earth is losing it even currently at some small rate. And this idea that these molecules have very different behaviors in early atmospheres allowed us to link how much hydrogen loss occurred to how much molecular hydrogen was present, because we think that water was nearly retained by Mars. And so by connecting the amount of hydrogen loss to a measure of an isotopic measure of fractionation of loss from the atmosphere, we could constrain how massive this early atmosphere was. And the number turns out to be about 10 bars, so 10 times as massive as Earth's atmosphere, nearly.
All right. So this is a very dense atmosphere. Is that the same type of atmosphere we have on Titan in terms of pressure?
Titan has similarities to this atmosphere. Of course, Titan's atmosphere is fairly dense, although not as dense as 10 bars. It's a little over a bar, but it does have other similarities in that it has a lot of hydrogen. We're familiar with methane on Titan forming the lakes on the surface, and also being lost from the atmosphere as hydrogen. And what's interesting about this story about early Mars is that the hydrogen that was there in the atmosphere would have also reacted with carbon species like CO or CO2 to form methane. And so we think, we're used to thinking of Mars as a planet that has a CO2-rich atmosphere. But actually, if the very early period involved in a hydrogen-rich atmosphere, then even carbon would have been in the form of CO or methane. And so it's in this sense that we think that early Mars was sort of a warm analog to Titan, that it would have had methane, it would have had these hazes, this would have been a hazy place potentially. It potentially would have been a site for organic synthesis like occurs on modern Titan. And so from this perspective of prebiotic synthesis, I think it's really interesting to think about and develop.
Before I go to my questions, thank you very much for people who join us from Copenhagen, Porto Alegre in Brazil. So many places, I can read all of them. Portugal, Leeds, England, St. Mary, Ontario, Chicago, the Bay Area, San Francisco, not too far away from here in Michigan. So we're talking about the past of Mars and whether or not Mars was an habitable place a few billion years ago. How many billion years ago are we talking about here?
So yeah, I'm glad you asked that question, because when we think about early Mars, a lot of what happened on early Mars was 4 billion years ago. The valleys and so forth, a lot of the features that Mariner found and we've been exploring. But here we're actually thinking about something even earlier. So Mars, we think, formed in a few million years after the solar system itself formed, the sun formed. So we're really talking about 4.5 billion years ago.
Billion years ago. All right, that's even before life appeared on Earth.
Or the Earth itself appeared.
Exactly.
So
that's
this
an interesting point. So you're telling me, to simplify, I'm simplifying, okay, that's my role, that 4.5 billion years ago, Mars could have been habitable in terms of the temperature on the surface. So are we talking about having ocean, water, liquid water as well?
Yes. we are talking about an atmosphere that can provide greenhouse warming to, say, 400 Kelvin, 500 Kelvin. These are temperatures that are very hot, or at least warm.
Mm-hmm.
And on Earth today, water would boil at these temperatures. So what would keep it from boiling would be this high pressure of this massive atmosphere. And so indeed, there is a possibility for warm to hot oceans. And it's not exactly clear whether this would have been a northern hemispheric ocean. Today we have this giant basin in the northern lowlands of Mars, and it's easy to imagine it being the site of an ocean. But actually, some of the models for how this basin formed are by impact around this same time. So this ocean could actually have even predated this hemispheric dichotomy, as we call it on Mars, the formation of this large basin in the north, or it could have postdated it. We don't know. It's sort of, this is part of what we're trying to understand is what was the mass of the ocean, what was the timing of its formation relative to the formation of the topography in the Martian crust. And so we don't exactly know what this reservoir would have looked like. What we do know is that it was there and could have exchanged with hydrogen in the atmosphere. So I said earlier that water would not escape from the atmosphere of Mars, but hydrogen could. And so by interacting with this hydrogen atmosphere, it could retain a memory of that early atmosphere, and that's what we think we've identified.
Okay, so a very warm ocean on the surface of like 200 degrees Celsius, basically, what you described. So what happened? Why Mars became such a desertic planet, cold and with such a thin atmosphere? What happened to this atmosphere?
So there's a couple ideas. One is it's the default idea that hydrogen is the lightest gas. It can rise to the top of the atmosphere and be exposed to photons from the sun and be lost to interplanetary space, interstellar space, ultimately. And that surely happened. It's still happening. But another possibility is actually that this hydrogen reacted with carbon species like CO2 and CO and formed methane. And the methane experienced some sort of evolution, like occurs on Titan. And so a lot of this organic matter could have actually rained down on the surface of Mars during this very early period and could have been retained, for all we know, partially in some parts of the Martian crust and the Martian record. And so I think from the perspective of our modeling, we can't really distinguish what happened to the hydrogen, only that it was lost. But in terms of the possibilities for life and prebiotic chemistry, it very much matters what happened to it.
So if we dig on Mars, some places, we may think, if we dig to the point where we can reach the 4.5 billion years ago, we may find some organic material buried under the surface?
That's the idea. And we are at the point in Mars exploration where we are detecting, organic matter in Martian meteorites, and we are detecting, trace amounts of organics in situ by the rovers. And so I think what we're adding to this conversation is a new source for these organic materials that we have to consider, that they really date back almost to the beginning. And I think an important step forward will be figuring out how to distinguish organic matter that was formed at the beginning versus organic matter that was synthesized potentially later.
Okay. So someone asked Anshu, we may post a question here. So she asked if there was organic matter, some people understand that there could be life, right? So where is this remnant of life on Mars?
That is the question. And I think, NASA has had this mantra of follow the water, and that takes us, to the habitable environments. But the natural next step is, where is the organic matter, and how can we find signatures that will help us find it? And so, this is the question that we're grappling with. And there have been, this field is obviously full of false starts. The methane story, the Mars methane story, where there were claims of methane in the Martian atmosphere, could be, if Mars, if methane is ultimately found unambiguously on Mars, that could point the way to sources that, point to organic matter in general, not just simple organic molecules.
Mhm.
And this is something that happens on Earth. It's not a crazy idea, but these are the questions that we're grappling with.
Okay, there was a paper recently published by a French group led by, I forgot his first name, Sauterey, where they claim that microorganisms could have changed the atmosphere of Mars. So can you tell us how this is related to your research?
Yeah, so so they looked at, the French group looked at a later period of Martian history where it was a CO2-rich atmosphere, and the climate was effectively being driven by outgassing of H2 or methane in sort of a transient or steady state fashion. So a little bit of H2 comes out, and then that H2 subsequently escapes, and it's that small abundance that's putting you just above giving you just enough greenhouse warming to make the surface stable to brines, for instance. And we're looking at a period of time that is much earlier, and it's not clear whether life would have arisen in the time period that we're looking at. We don't know actually how quickly life arises, and so the possibility that there is this environment early on that's conducive to the origin of life, I think, brings that question to the fore. If we do ultimately find life on Mars, I think it could tell us something about how quickly it formed, because it would have to be in that very early period, however long it turns out to be. But if there was life on Mars, then there's no question that, like life on Earth, it would have interacted with the atmosphere, exchanged gases with the atmosphere, and changed its environment. And how that interaction, plays out, I think, is still something that we're trying to sort out.
Okay, we have a lot of questions, and you may not be able to answer to all of them because I'm looking at them. They're very, very diverse in topics and stuff. But I have one from Ron Schneider right now. We can post it. Cool, very deep caves contain liquid water that has cave-dwelling creatures like blind shrimp, little fish, and so on Mars.
Yeah. So when we're talking about life, I think we're talking about life as it occurred on Earth for the first 3.5 or 4 billion years, microbial life. I think to go from microbial life to multicellular organisms and ultimately, large megafauna, I think is, requires potentially very special circumstances. So I think I would want to first find evidence of microbial life before, thinking about how complex the life could have evolved in the time that it had. But certainly it's true that on the surface, there's a lot more energy that's available. And so I think if one were to make a living by, eating rocks like some microbes do, it's very difficult to support, the kind of high energy lifestyle that we're used to on the surface of the planet. So if you don't have access to sunlight, I think it's going to be very difficult to have, a high energy lifestyle like we enjoy.
Okay, a complex question, but Nikki Perefogon She's asking if the analysis of sample from Phobos, that's the mission MMX by JAXA, could help studying ancient Mars. Can we learn something by getting to Phobos or Deimos and picking up a sample of the moon about Mars itself?
Yeah, I think the answer has to be yes. Part of the rationale, I think, is indeed that Phobos records. Phobos may have formed during this early period when this atmosphere was around, and it may have recorded some remnant of the atmosphere, in this very early period. And so it could be that we'll learn about the atmospheric composition, for example, in a way that we couldn't just by looking at rocks on the surface. So absolutely, I think that's a very promising line of inquiry.
Okay. The issue of the magnetic field. James Faber asked, how long ago did Mars lose its magnetic field? What is the consequences of that for the formation of life?
Yeah, so we know that Mars had a magnetic field very early on, and around, after 500 million years or so, it lost it. And, it's actually not clear exactly what consequence that would have for the atmosphere, which is certainly important for life. We tend to think of the magnetic field as, shielding the atmosphere from the solar wind. But actually, in the scenarios that we're looking at, the gases that are escaping are oftentimes neutral gases. So they don't actually see the magnetic field. And there are other models that think that the magnetic field actually promotes the escape of gases that do get ionized. And so I think the magnetic field question as it relates to atmospheres certainly is very much an open question. But in terms of radiation on the surface, of course, that is something that a magnetic field could help to protect.
Okay. You're trying to answer to a big question here. Is the past history of Mars and whether or not Mars was habitable in the past. What is your involvement in this research now? You publish papers over the past 5 years. What's your new work on this? What are you looking forward?
Yeah, so I'm currently working on this model and this very early period and looking for testable predictions that we can make. When we started working on this problem, the data was already there from meteorites, from spacecraft, and it was just the question of putting these pieces together into a coherent and testable story. And so I'm continuing to develop this in the hopes of making predictions that can then send the ball back into the court of observers, people in the laboratory, and people building instruments to study Mars. So the idea is to develop this story in a way that it can be tested and developed going forward.
So you are, how do you call yourself? You're a theorist, you're a modelist, you climate, how you describe your work?
I identify as a planetary scientist. Or a planetary physicist, depending on the situation. But I try to also incorporate chemistry or isotope geochemistry into my work, because I think it's important for us theorists to be grounded in data, and that's something that I'm hoping to also keep in the models that I'm building in the future.
Okay, are you expecting some interesting new data coming from future rovers like ExoMars?
Potentially, yes. I did notice that some of the data that we used in this model were meteorite data, and other data were spacecraft data. So it really is bringing sort of disparate, pieces of interrogation together. One area that hasn't, I don't think, gotten enough attention in regards to remote sensing is, we have this paradigm in planetary science where we say, well, early Earth is not very well known. A lot of the evidence was destroyed, so let's go and study Mars. And I think that's a very strong rationale. But there's also another rationale that's now just emerging, which is to say that early Earth and early Mars are not very well known. And so let's go study analogs of young exoplanets. And there are people that are looking for young exoplanets now in the Kepler and TESS populations for this very reason, because we expect the early planets to be very different than the planets when they mature. And so it's a very formative period in the life of these planets. And so I think having an exoplanetary perspective on Mars is something that's going to emerge also in the near future.
Yeah, that's a very important point, is that now we're discovering more and more of those exoplanets. And because of the stars of those exoplanets at different age, sometimes we have very young exoplanets. So we can see the past of our own planets, terrestrial planet, by simply looking around and looking at this young proto-Mars or proto-Earth, whatever you want to call them. So maybe find something which has this kind of atmosphere you just described, made of mostly of molecular hydrogen, high density, and maybe measure the temperature one day on the surface of those planets to see if they're truly warm and have a liquid ocean.
Right. That's the sort of impetus. Of course, there are challenges because of the small mass and so forth. It's not what JWST, for example, was built to do. But you also get, you do get advantages because these atmospheres are evaporating, and so the cross section for observing a planet that's losing this atmosphere and wind is much greater than a planet like Earth, which is holding onto its atmosphere very tightly. And so there are legitimate trade-offs that you have to work through to figure out when this type of planet will be detectable.
All right. Well, thank you very much, Kaveh, for your time. We're reaching the end of our 30 minutes. I hope to see you soon in person, maybe at the SETI Institute or another SETI Live, or maybe a SETI talk to talk about your research. Thanks again. To all our viewers, this was a SETI Live on Mars and the potential of Mars being habitable in the past. We are the SETI Institute, a non-profit organization dedicated to search for life in our universe. You can support us, support this program specifically in communication and outreach by going on in our website, seti.org/give now. I think that's what it is. You can make a small donation to support our researcher, our outreach and communication team. You can also simply like this video, post comments, tell us about what you think about it. Join our also newsletter called Journey. You will find out what's going on about in the world of astrobiology on a weekly or monthly basis based on your preference. And stay in contact with us. Join us on all the social media. We are Twitter, Facebook, etc., and join the conversation. It's a wonderful time to be an astronomer. And I think it's a wonderful time for people to follow what's going on in the world of astrobiology. So thanks again, Kaveh, and we see you soon next week for a special SETI Live for Halloween and another SETI Live that I forgot about, but I'm sorry for forgetting that best. But anyway, see you next week. Bye-bye.